Привет, я Никита Калинин, и в рамках лекции про топологический анализ данных мои друзья расскажут то, как топологический анализ данных применяется в их области. Сейчас Пратюш Пранав расскажет о том, как топологический анализ данных применяется в космологии.
So today I'm going to tell you about the use of geometry and topology to understand how structures form and evolve over the timeline of the universe. And we will actually talk about all the stages of the universe, where this picture shows what happens, what we understand of what happens in the universe across its timeline. According to the current theory, which is the Big Bang theory, in that sense that the universe starts in a hot, dense state, and this is called the hot Big Bang model. Then up to around 375,000 years after Big Bang, the universe is opaque to us in the sense that we cannot really see. Like up to this point, there is no free light in the universe. There is no light, so we are not able to see. Like the light from that part is not able to reach us, so we do not understand what happens at that. But there is no direct observation of that part of the universe. But around 375,000 years after Big Bang, the universe cools down. There is a process. The reason why there is no light in the universe up to that time is that the universe is very hot. And when the universe is very hot, then all the protons and electrons, they exist in a plasma state because the light photon particles are energetic enough to knock into a hydrogen atom so that they do not form a proton and electron do not come together to form a hydrogen atom. So this is an equilibrium reaction that the moment a hydrogen atom forms, a neighboring photon with sufficient energy knocks into it and makes it into a plasma. So, but because the universe is expanding, this is one of the things that we observe in the universe, that it is expanding. So if it is expanding right now, we can extrapolate that it also started expanding at the time of Big Bang. So because the universe is expanding and the content at the time of the universe can be approximated as a gas, and expanding gases cool down. So at some point it reaches a stage where the photons don't have enough energy to knock an electron out of the hydrogen atom anymore. And this is when the photons from the Big Bang, the early created radiation, this is when it gets free and starts streaming freely in the universe. This is when the universe becomes transparent to light. And since then we can observe. So our earliest observation of the universe is the moment of the cosmic microwave background. This is called the Epoch of Recombination. This is when the atoms, the protons and electrons recombine together and release photons. Now the interesting thing, so a part of my research concentrates on studying the property of the cosmic microwave background. I will show in the next slide. So if we have measurements of the cosmic microwave background, this is the observed map of the cosmic microwave background from the satellite that we sent in the outer space. This is the Planck satellite, the latest satellite that measures the cosmic microwave background. We send it in the outer space because it's easier and the observations are more clean. And you would see that there are... Sorry?
What is a microwave? What is that?
We will explain what the cosmic microwave background is. We will go into that in a second. I will go there. So, or we can talk about it now. So the thing why it is called the cosmic microwave background is at that time, this actually, the light that we observe, the light that we see, which was released at the Epoch of Recombination, it's a black body spectrum. It is actually the most perfect black body that we observe in the universe. And at that time when it was radiated, it was very hot. It was not in the microwave region. The wavelengths were not in the microwave region. But because the universe is also expanding and things are cooling down, the temperature of the cosmic background, it also cools down. It cools down things, so it comes in the range of microwave wavelengths. but it was in the ultraviolet, probably very hot objects, like they have higher the frequencies. Hotter objects are associated with higher frequencies, and so stars which are very hot, they radiate in ultraviolet. So, but as things cool down, their radiation, the wavelength starts getting elongated. And at the moment, the wavelengths of the cosmic microwave background, this photons that were released at the epoch of recombination, at the moment, their wavelengths are in the microwave region. So we call them the cosmic microwave background. Like the cosmic microwave background, there is also a cosmic infrared background. There would be also a cosmic neutrino background, if neutrinos were to be there. So there are many backgrounds. All the radiations that we can virtually observe from the time of the start of the universe, around the infant universe, these are all examples of background radiations. And cosmic microwave background is in the visible range, or the microwave range actually. And this is the first thing that we can actually observe in terms of light. So this is the earliest observational probe of the happenings of the early universe. There is nothing early than technically there could be a cosmic neutrino background, but we are not able to detect cosmic neutrinos so well. Even neutrinos from our sun, it's very difficult to detect. To detect the neutrino from the start of the early universe, it's a very challenging task. So we concentrate on the cosmic microwave background. So the universe becomes transparent at the cosmic microwave background. You will notice that up to this point, there are no structures in the universe that we see. So up to from here to here, we call the cosmic dark ages. This is when there is only gas, nothing happening. There is no radiation except the photon radiation that went up. But at some point now, the gravity is also acting. So all these gases, they start to collapse together under the influence of gravity. There will be clumps where the gravitational potential is higher than the background gravitational potential. So this place will start attracting more gas. Slowly, gases, they will start attracting at the peaks of the gravitational potential, or the surrounding matter starts flowing into. And at some point, the collapsing gases, they become hot enough, because gravity also causes things to collapse, and this causes things to heat up. And eventually, the force of gravity acts like it becomes so dense that it lights up. This is when the reionization happens. This is called the cosmic dawn again. That there was the cosmic microwave background, there was a dark age where there was no light. And then, because things are again clamping up, the stars form, the galaxies start lighting up. This is the epoch of reionization again. And this is when things start lighting up again. After that is when the galaxies start evolving, and we see all kinds of structure in the universe up to the present day. But we see that there are structures in the universe, and our current theories, we think that these structures, they evolved from the density perturbations in the very initial universe. Like it was all very uniform, but because it was very hot, there were quantum perturbations in this space-time, in this spatial region. And these perturbations, the peaks of these perturbations, later resulted in matter accreting together and forming later structures. And actually, so we think, and this is imprinted in the cosmic, the information of this field, this matter field, the properties of the stochastic matter distribution in the early universe. This is imprinted in the cosmic microwave background, because so our theory of the current standard theory of the universe says that the standard thing is we start with a homogeneous and isotropic universe. So that, because this is the Copernican principle, that we are not a special thing in the universe. Every place should look same enough in all the directions, if looked all far enough, sufficient far enough. So this is one of the assumptions that we take about the universe, that it is homogeneous and isotropic. And if it is homogeneous and isotropic, But still we see that there is structures in the universe. So it is not totally homogeneous. There is something going on. And this we explain by saying that there were quantum perturbations in the very hot, early, dense isotropic medium that the universe was in. And these quantum perturbations are the result that they amplified later by the action of gravity and result in structures later. And then because this is a quantum perturbation, this is a stochastic field basically. These perturbations in the otherwise uniform matter field distribution, this is a stochastic process. And so we try to study the properties of the stochastic matter distribution. And the interesting thing is that at the time when the light of the cosmic microwave background was released, then the photon, which was sitting in the gravitational dip potential, it had to spend a little energy to climb out of that gravitational potential. So it loses a little energy and it gets redshifted. When a photon loses energy, it gets redshifted a little bit. Like many things would happen at that time. So the result, the combination of these things means that all the regions in this observation of the cosmic microwave background, here you see a color map of the cosmic microwave background. The orange areas are where the temperature is higher than the average temperature. And the blue regions, the red and the blue regions, basically. Blue regions are the regions where temperature is lower than the background average. And this means that the blue region corresponds to a dip in the gravitational, this is a minimum of the density field, the matter density field, where the photon, this is the reason why there is a dip there. The red region is the maximum of the matter density field. This is where, so like the cosmic microwave background also maps the matter distribution of the early universe. This light map, the light map, the fluctuatory light map that we see, the stochastic light map, it is the map also of the matter distribution in the universe. So if we study the properties of this light map, we are also indirectly studying the property of this background stochastic density field of the matter in the early universe. So this is one part of my research. This is the studying the light of the early universe, the cosmic microwave background. The other part of my research concentrates on the late time of the universe. All of these ideas, late time of the universe, meaning we try to study the structures that we see in the universe in the current days. We look at the galaxy distribution. We have observational data. We look at the galaxy distribution in the universe, and we try to understand how the galaxies are distributed. What are the properties of this galaxy, the matter distribution in the current universe? And the broad goal of these exercises is to be able to trace the evolution of the cosmic history. This is the mega broad goal in general of the cosmological astrophysical community, to be able to understand how the universe formed and evolved. And so we would measure the current universe, things from the current universe and things from the past universe. And we try to see if our measurements match. And if they don't match, then why not? And if not, then we try to refine our models of how we understand is the matter distribution in the universe. And from that, how and why the universe has these, what are these properties of the universe in general. I will take a little digression and tell you also about the nature of the fluctuations in the matter distribution in the early universe. I will take a pause a little bit and we can edit it out if needed. There is a theory, one of the standard theories, the cosmological standard theory is called the lambda cold dark matter paradigm. This is the LCDM cosmology. This is our standard cosmological paradigm. Each of these things have a meaning. The term lambda refers to dark energy. So our standard model, when we look at the content of the universe, the energy content of the universe, if the total energy, let's say, is 100, then from our measurements, we find that only 4% of that total 100 is contributed by the visible baryonic matter of the universe, which is all the things that we can see in the universe. So for example, the galaxies, the stars, all these things that glow, these are the baryonic matter in the universe. And we, from our current models, if our current model, we think that our model is correct, then our estimates of the matter distribution, the baryonic matter distribution, this comes to around 4% out of that 100. Around the rest of the 26 or 27% is something that we see that there is a gravitational interaction going on, but we have no other clue about what this thing is. We call this the dark matter because it shows there is an effect of gravity. But we have no other information about it except that it interacts gravitationally. It has no emission, no light. So we do not really know what it is, but that there is something going on. There is an additional matter in, if our current models are correct, then there is additional matter in the universe which we are not able to see, but it is affecting things gravitationally. Around the rest of the 67% is something called the dark energy, because we also see that the universe is expanding. If gravity was the only thing, gravity is an attractional force. So if gravity was the only thing in the universe, then everything would have collapsed together at some point eventually. But we see that the universe is expanding, and it's also accelerated expansion at the moment. This is what got the Nobel Prize, the recent Nobel Prize. We saw from supernova measurements that the universe is expanding, and not only expanding, the expansion is accelerating. This means there is something else, some other thing happening. And this expansion, this we credit to the dark energy, which is what is the lambda term in the lambda cold dark matter cosmology. And this has its root from the days of Einstein, actually. So when Einstein gave his theory of general relativity, and when he solved his equations, he saw that the universe came out. The solutions to his equation was an expanding universe. But at that time, we did not have the observations of the universe and the standard theory that was prevalent. So this actually is very interesting, how we change our theories, how observation, how the scientific process changes across history of time, like how we change our opinions based on our observation. So philosophically, human mind likes to think about infinity. And when we looked into the sky before the advent of the telescope, where we could look beyond our galaxy, the nighttime stars in the skies, they looked constant, except even before, when people looked at planets, they were changing speed, they were changing positions really fast. This is how they found out these are planets. But the rest of the thing, the stars were relatively constant in the universe. So a general thought was that the universe was in a steady state, that it had no beginning, no end. It was what it was. It is in the same state forever, always. So when Einstein found out that his solutions to the general relativistic equations applied to the whole universe, gave an expanding universe, he called it a blunder. He could not reconcile it. He could not accept that the universe could be expanding, because the general thought was the universe was steady. So he adds this lambda term to this expanding universe solution to give it a constant universe solution, which he at that time said was his greatest blunder, adding this lambda term, because the universe was supposed to be a constant. So he thought his expanding universe was actually a wrong solution. But later, as we came into observations, it turned out that he was right all through the way, that the universe is actually expanding. And this lambda is not actually a blunder, Einstein. This is actually Einstein. This is called actually the most famous blunder, which is not the blunder actually. So this is the background of the Einstein equations. And now if the universe is expanding and all things happening, then there are a few problems. The problem is that the solutions to the Einstein equation, they could admit three kinds of spaces. One which is a flat space, the other which is a negatively curved space, and the third which is a positively curved space. But when we measure the curvature of the space, we see it is flat. Then the question, one of the questions that the basic fundamental question of cosmology is called the curvature problem. It says, why is the universe flat? It could have been positive, it could have been negative. So one of the answers, the other problem is the monopole problem. The monopole problem says, if we look at the electromagnetic, the equations of the electromagnetic radiation, then we see that they are symmetric in electric and magnetic terms. But we see that there are no magnetic monopoles, in the sense that we only see magnets where north and south, they come together. If you divide a magnet, it will still be a clump of north and south. North does not go separate, south does not go separate. On the other hand, electric charge, electric monopoles exist. A proton is a positive charge, an electron is a negative charge. So electric monopoles exist. But we haven't observed magnetic monopoles, in the sense north separate, like sources of north or sources of south pole. Why not? If the electromagnetic field is symmetric. To answer all these questions comes a theory which actually has not been verified, and it is very difficult to verify this theory. And this can also lead into philosophical questions about what should be a valid scientific theory. So we say that the valid scientific theory should be something that should be testable, but we do not go into it. The standard theory which answers all of these questions is the inflationary theory of the universe. So inflationary theory says, right after the time of Big Bang, if t equal to 0, if we call t equal to 0 is the Big Bang, then right after Big Bang, in a span of about 10 to the power minus 27 seconds, things that were of the size of 10 to the power minus 34 meters become the size of the galaxy, which is around 100,000 light years. So light takes 100,000 years to go from one end to the other end of the galaxy. You can imagine what huge size that is. So something which is very minuscule, which is actually the limit of the Planck length, 10 to the power minus 34 meter, which is the smallest from the Planck quantum mechanics. This is the length scale that we are talking about. So Planck scale blows up to the size of a galaxy in an extremely small time, which is 10 to the power minus 27 seconds. So the result of this procedure is that it flattens out all the curvature of the universe, at least. So this theory at least explains why do we observe the universe flat. And because this expansion is very rapid, it also freezes the quantum fluctuations that were at the time of Big Bang, which later results by gravitational amplification into the structures that we see in the universe today. And then it also says nicely that because the universe expanded rapidly so fast, the volume became so large, the density of the magnetic monopoles became so small that in our vicinity, we just don't observe anything. I mean, there is no proof of this expansion, this inflationary era of the universe, but because it conveniently answers a few things, we take it for now too. But there are debates about whether we should accept the inflationary theory or not. Like there is debate about another very popular theory, string theory. String theory answers a lot of questions, but whether we can test it or not is a very tough question. Moreover, on top of that, string theory is flexible enough to be able to accommodate all the questions that we ask. You just change the model a little bit and everything. So whether these things, but this is a question of philosophy. We do not go in there. Now, this is the early universe. And so like this expansion of the universe and this expansion of the phenomena, this results in a certain spectrum of the power, the fluctuations of the matter distribution. And in the most simplest form, we say that these fluctuations are an isotropic and homogeneous Gaussian random field. This is the end result of the matter distribution that comes out of the standard result of this is the standard result of the standard cosmological paradigm. That the power distribution, the fluctuation of the power distribution of the matter distribution in the early universe is an isotropic and homogeneous Gaussian random field. The stochastic field, the stochastic matter field is a homogeneous isotropic Gaussian random field. So now our observation, the questions that we could ask is that we look at the observations of the cosmic microwave background and we compare it to the theoretical model, simulations based on the theoretical model, which would be an isotropic and homogeneous Gaussian random field. By the way, the measurement of the cosmic microwave background, this is the map. And the fluctuations here are of the order of 10 to the power minus 5 kelvins, where the background temperature is 2.7 Kelvin approximately. So these fluctuations that we measure are very minuscule, and this satellite has to be very, very precise in being able to measure, first of all, this background temperature of 2.7 Kelvin, which is just 2 degrees above absolute zero. And then the differentials of around 10 to the power minus 5 Kelvin over this background that we have to measure. That's one of the reasons also why they send the satellite in the space. So there is no interference from the background. But still, we are not able to measure all of the cosmic microwave background in its entirety, because you can imagine we are living in a galaxy. This is not an imagination. This is a reality, actually, that we live in the galaxy, and our galaxy has a thin disk-like shape. So in the plane of the disk, which is a little bit thick, it is actually very thick. It's of the order of a few kiloparsecs, which is a few thousand, maybe 1,000 light years or something. So this disk obfuscates the observation in its equatorial plane. Also, there are other objects in the foreground, which are very bright, for example. Then they also interfere in the measurement of the cosmic microwave background. So this is a visualization, for example, of the cosmic microwave background, where the galactic disk has been masked out. Also in the north and the south galactic pole, there are regions where there would have been a bright foreground object, a quasar maybe, or a group of galaxies which interfere in the observation. Then we mask out these regions, and we look at the regions which are left then. And how do we look at is the second part of the talk, which we already are familiar with, and the reason for this little presentation. We look at these things, we look at these fluctuations with methods from algebraic topology, which is the Betti numbers. We compute the Betti numbers of the level sets of the cosmic microwave background observation. And the idea is to be able to compare these topological measurements, these quantities that we measure on this manifold, which is the two-dimensional sphere, minus the masked out region. We look at these things and we measure these topological quantities. And we also measure these topological quantities in the simulations that we have created, assuming certain things about the model, and which is the model which we have been talking in the last few minutes, and which gives the matter distribution to be a Gaussian random field, an isotropic and homogeneous Gaussian random field. So we make our simulations based on the fact that the universe or the cosmic microwave background is an isotropic and homogeneous Gaussian random field. And then we compute the topological quantities from the simulations. And then we compute them also from the observed sky. And we try to look at if they match or mismatch in order to verify or validate the hypothesis of the standard model. And interestingly, what we see, like, these are first results of its kind, because usually all the methods that we have employed till now, they have not shown much difference between the simulations and the observations. In the sense, the Minkowski functionals, for example, they do not show so much difference. They show, like, if we computed the Minkowski functional of the cosmic microwave background, we see that the simulations and the observations, they actually match very well. But when we look at the Betti numbers, we see that there is actually a mismatch between the observed and the computed Betti numbers, which goes even up to 3 to 3 sigma, more than 3 to 3.5 sigma at certain scales, if we smooth the sky also. So this is another thing, that we look at the CMB sky and we smooth it at different angular scales, because we expect that different angular scales have also possibly different mechanisms. It is quite possible that they are not the same field always. Why? Because, for example, if we look at the cosmic microwave background and if we do the computations, assuming our current model, then the horizon of the sound, which at the early time, in the early universe, the the medium, the speed of the light and sound, it was an acoustic medium. So the speed of the light and sound were the same, which was very high actually. And so speed of sound in this early acoustic medium, like this puts a limit on the horizon, the size of the horizon, meaning if you are at this point, what is the maximum radius up to which you can communicate? So because the universe is also expanding, things are also going away from you. So the things that you can communicate are things only from where light can come to you. And this horizon is approximately around 1 degree at the cosmic microwave background. So things which are more than a degree separated at the CMB sky, these are causally disconnected. Means that information could not have passed from one region to the other region over there. So they do not have a reason to be thermalized. They are not in contact, they are not in communication. So this happens beyond 1 degree. So if there is an underlying background physical thing that was happening in the early universe, then we expect its imprint to be in the super horizon scale of the field, the cosmic microwave background field. So if we smooth beyond a degree or 2 degrees is when we are in the cosmological regime of the universe. Within a degree, because gravity is also acting, there is mode coupling happening. Like there are also, because gravity is acting, it also dampens the fluctuations, the modes of the matter distribution, because things are collapsing and all the matter modes within this thing, they are coupled and they are damped. So there are physical processes within a degree scale that we need to take into account that would also introduce non-Gaussianities in the field. So all these things happening. So we look at a scale of, basically we look at different scales by smoothing at different degree, different angular scales, the data. And here, so for example, we look at there are 8 different smoothing scales, meaning 8 different resolutions that we look at in the cosmic microwave background. And there are 4 different cleaning methods of the observational data. And we compare it to 1,000 simulations, and then we compute the standard deviations. And we notice that the difference between the simulation and the observation are more than 3 to 3.5 sigma at some scales, which is beyond a degree scale. So we are more in the cosmological regime. Now, these are very interesting results if they were only correct always. If we had a way to be totally sure that they are correct, that there could. So now we have to also think that if we find something, the scientific procedure actually tells us that we should not always say that, oh, we found something first. Like we have to make sure that all the sources, we have accounted for all the possible sources of error. And when we measure the cosmic microwave background, which is the very early universe, there is a lot of things that could be a possible source of error in this measurement. There is the intervening matter distribution, which could act like lenses, gravitational lenses, and they could distort the microwave background characteristics. On top of that, there could be instrumental systematics. There could be the measuring instruments itself may have some random errors. So all of these things, we need to be very sure if this is correct or not. And once we have made sure all of these things are correct, we can say that if nothing else is causing the problem, then this should be the early universe. But this is a research which is in progress. This is an investigation that's going on. We have to make sure that all the possible sources of errors are discounted. Is when can we only say that this is a truly cosmological, novel result. But they are giving interesting directions of research. And this is my research in brief, nutshell.
Good, good, very good. So please show us these nice pictures on the last slide.
Okay, so now this was the cosmic microwave background. This is from the early universe. This is what we studied. The next part of my work involves trying to study also cosmic structures. If we look at the universe from a few to a few hundreds of megaparsecs from our vantage point, we see that matter is actually arranged in a web-like pattern, which we commonly call the cosmic web. It actually looks like a 3-dimensional spider web, and it has clusters where there are roughly spherical shapes which contains thousands of galaxies, which we call clusters of galaxies. These are the most dominant shapes of the cosmic web. Then there are wispy, filamentary, one-dimensional tube-like structures, what we call filaments. Then we also observe galaxies distributed in quasi two-dimensional structure, which are thickened actually. These are which we call the walls. And then we also find the empty voids, which are bereft of any matter at all. And this is what roughly comprises what we call the cosmic web. And to be able to understand the properties of, let's say, the matter distribution, for example, how would galaxies form and evolve? You can imagine that if the galaxy is sitting in a cluster with a lot of other galaxies, and it's like thousands of galaxies, they evolved from a cluster, for example, then their evolution history would be different from a galaxy which is sitting isolated in the middle of an empty void with no other surroundings. Because a cluster region is a busy region, so there would be tidal interactions between galaxies. If a galaxy comes very close to another galaxy, there could be tidal stripping of stars. So it has a violent, not very stable history of evolution in a very busy region. But if we are in a non-busy region, this galaxy would evolve in a different way. So to be able to understand how different kinds of galaxies evolve in the universe, we should be able to also detect these structures first. So to be able to understand how galaxies evolve, we need to be able to identify their surroundings, whether this galaxy is sitting in a cluster or whether it's sitting in a filamentary region or a wall region or in a void. And depending on that, we can try to understand how these things evolve. And here again, topology comes in a very handy, nice way, because topology gives us methods for segmentations of scalar fields. And these segmentations, they naturally correspond to the elements of the cosmic web that we see. So roughly, we can construct something called a Morse scale complex of the galaxy distribution, for example, assuming that each galaxy is a point. On that large scales of things, we can, this is a valid assumption that each of these galaxies we assume as a point. So for example, here you see a part of a cosmological simulation, where we see a lot of structures, and each of these points is a galaxy, in fact. And there are millions of galaxies that we evolve in a simulation. And then we see that, of course, obviously, it is full of rich structures. There are spherical blobs around, which is what we call the cluster-like regions. And then we see elongated, one-dimensional, tenuous, wispy, thin structures. This is what we call filaments. There would also be two-dimensional structures, which would be wall-like. And then there are basically the more empty regions, which we call the voids. And we try to identify one-dimensional filamentary regions in all of these dense versus non-dense regions, because ultimately we want to see how these regions are characterized. So we try to, for here, we look at 3 other pictures where we have extracted the filamentary structures of the cosmic web simulation by constructing a Morse-scale complex, which segments this thing according to the characteristics of the density field. So if there is a particle distribution, then we can assume that it comes from an underlying density field. We sampled this particle from an underlying density field. And this field would have maxima, minima, saddle points, and all these things. And a Morse-scale complex decomposes this field into things which are consistent by identifying these critical points, these maxima, minima, and saddle points, and the overlapping regions. I do not go into details because this is a high school talk. So there we can identify overlapping regions which can form as the building blocks of this Morse-scale complex, where the flow is in the same direction always. And they meet together at the critical points, which are the maxima, minima, or saddle points. And so together, these objects, they form the partition of the domain, and they correspond to the structures that comprise the cosmic web. So once we have identified the elements of the cosmic web, meaning the clusters, the filaments, the wall, and the void, then we can go further deeper and look at the galaxies that are there and try to correlate the properties of the galaxy. For example, is it a spherical galaxy or an elliptical galaxy? We see a lot of different morphologies in the galaxy shapes in the universe. There are spherical galaxies, not spherical, we rather call it elliptical galaxies. Total perfect sphere is not really possible because of things happening, but it has some sort of a little bit of eccentricity. So there are elliptical galaxies, which are roughly three-dimensional blobs. Then there are very thin galaxies, which we call spiral galaxies, and they have spiral-like arms. And why they form and how they form, or why a galaxy evolves into a elliptical one, or why it evolves into a spiral one, we do not really understand why these things happen. So for example, the galaxy that we are living in, our Milky Way, is a spiral galaxy. It actually looks very beautiful. It has all these spiral arms going through. We can even see it in the sky, one of these arms. So the idea is to be able to understand how these things evolve and why are we living in such structures and how these structures form and evolve. And topology can be a very nice tool, topological data analysis, as I showed you in these past few slides. It has used in all these stages of the evolution of the universe, various tools that come out of topological data analysis or computational topology. They can be used as analytical tools or tools for image segmentation and visualization as well. These are two very important components that they also result in very strong and nice visualizations that are based on solid mathematical theories, but they also give you analytical tools with which you can analyze your data in a new way and adds to the arsenal of tools that we have available, because there is new data sets coming up and that always needs new analysis tools to look into. Like a new tool is always interesting if it could show the other properties that other tools have not been able to capture. And this is the idea of topological data analysis, basically.
Yeah, thank you very much. Good, very good, very nice talk.